हो गया तो शुरू. Okay, Jivan,
Yes, sir.
you can start.
Hello. Okay. A very good evening to Professor Rukmi Datta. And because we know in Australia this evening is there, so and very good morning to all the participants from India. So I would like to welcome in the lecture 9 of the GIAN course, Advanced Permanent Magnet Machine Drive Technologies for Transport, Electrification and Renewable Energy. So firstly, I will give a very brief introduction of Professor Rukmi Datta. Professor Rukmi Datta presently working as an associate professor in the Energy System Research Group, School of Electrical Engineering and Telecommunications at the University of New South Wales, Sydney, Australia. So now I would like to invite Professor Rukmi Datta to start a session.
Thank you, Jian Jot.
Welcome.
Can I get the access to share screen, please?
Yes, Mother, you can do it.
Yes, sure, ma'am. Sure, ma'am.
Okay, so as usual, in the last couple of days, we always starting with looking at the quiz. So we'll do that same today as well, looking at yesterday's quiz. So the one item that has been identified as the difficult is design. Obviously, it is the design of the machine, especially of those who have been introduced to it for the first time. It could be a difficult concept. I'm hoping that today, after the tutorial, which again going to be on the FE software, first half at least, you will have some a little bit more understanding. So that's hopefully, and also by the end of this course, you will get or will have some more understanding about electric machine design. Then there were a couple of technical questions. The first question was actually about the pole pitch and the coil pitch that we discussed. These are actually classical concept in machine design. It's for all type of machine, not just relates to PMSM. Actually, the question, if you read carefully, it has swapped the definition of pole pitch and coil pitch. So if you do not read it carefully, then it's very easy to get the answer wrong. So actually the statement was false since the definition was swapped. And it appears that those who have read it carefully got it correct, but those who didn't, they make the mistake. So we have a 50-50 split in the answers, looks like. After that, we talked about how the pole numbers, magnetic pole numbers, influences the thickness of the yoke. And it looks like majority of you have got it correct. The yoke is inversely proportional to pole number. As the pole number increases, yoke can become thinner and thinner. Then we talk a little bit about concentrated winding, and the question was whether concentrated winding can give a sinusoidal EMF. And again, the majority of you got the correct. It is yes, we can get it. But remember that the concentrated type winding gives you non-sinusoidal MMF, magnetomotive force. However, it can give you sinusoidal EMF with certain pole number and slot numbers. Not for concentrated winding has limitation. You cannot use all combination of slot and pole. Okay. Then the other question was about it was a numerical problem from our tutor, Dr. Chu. And it looks like, again, majority of you have got the correct answer. It was calculation of an air gap, most likely, what I recall. So then other one was what affects the magnetic loading of a machine. There were, in fact, multiple answers for this question. And again, we can see that majority of you have got the 3 correct answers. Magnetic loading is affected by the allowed maximum saturation in the material. It also depends on the magnetic property of the steel, the electric steel that's being used, and how much iron loss you can allow. Because as we know, iron loss is function of magnetic flux and frequency. So, and the magnetic loading actually means the magnetic flux in the machine, okay? Then there was another numerical questions about calculating the, this one was about finding air gap, it seems. So in that question, again, most of you got correct answer, so that's good. So looks like at least some of the concept you are getting correct or having some understanding from the quiz results. That's what appears. So I'm glad that that's happening. So next, we'll start today's lecture. So I'll start sharing my presentation. Okay, so we are now today on the 4th day of our course. In the last couple of days, we were discussing a lot about the electromagnetism, basically, and how that relates to PMSM. So with yesterday's tutorial, you have got some idea how to start a design of a PMSM using analytical tool or using finite element. But if you may recall, in the finite element tutorial, what you have done is you only have the magnets there. You have the copper windings drawn in your picture, but you haven't actually excited those windings, okay? Or you haven't given any current to those windings. Now, what current should we give? How that depends actually on how to control the PMSM machine. So that's why today's course will be looking at how can you control a PMSM drive, and that will slowly give you the idea what current should in fact go to your stator winding, and how does it happens in a real system, which you will going to like simulate in finite element as a current source, okay? So that's why this topic relates to drives. It's not about design anymore. It's more about drives. And if we want to understand the drive or its control of the PMSM, the first thing we need is a dynamic model for PMSM. I mentioned when we discussed the fundamental theory of synchronous machine, the steady state equivalent circuit can only be used for steady state. But when you design control for a machine, it needs to work also during the transient, okay? So during dynamics, during acceleration, deceleration. So that means we need a model which can, or we need an equivalent circuit which can handle the dynamics. And that is the DQ model and DQ theory. I'm not sure whether some of you are familiar with it or not. Those who are doing power system research may be familiar with DQ axis, DQ theory, DQ transformation. This is very common concept required by the control control engineers relating to power system or even motor drive. But I'm assuming you know nothing, and that's why we start from very basic. So if there are anyone who knows it, hopefully it is going to be a refresher for you. So after that introduction to DQ model, we will go to the advanced control of a PM synchronous machine using field-oriented control. And then there is also more advanced control or sensorless control, which I probably will not be able to cover today. So I'm thinking we'll start tomorrow with that, and then we'll go to tomorrow's rest of the content. So first half, that's why our learning goal is to, you should be able to explain what is DQ theory and how it is important to motor drive. And then you should also be able to derive the DQ model for permanent magnet synchronous machine. Now let's start with something that we have already learned, the voltage equation of a synchronous machine. You may recall from our second day or first day lecture, that's voltage, phase voltage in the time domain equals to the resistive drop in the winding, synchronous inductance or voltage drop in the synchronous inductance plus the EMF, back EMF. So this back EMF in a PMSM comes from the rotor magnets. So the flux linkage that relates to the EMF is permanent magnet flux linkage, okay? Lambda PM we'll be using here. And the synchronous reactance, or sorry, synchronous inductance relates to the flux linkage coming from the current, okay? So that is shown as lambda DAS. So this is the flux linkage of the phase A current, which actually sum of the self-inductance time phase A current, mutual inductance between phase A and B time B phase current, plus the mutual inductance between A and C time C phase current. So we have learned about it. And this time domain equation, as you can see, it can be used for designing controller because it has dynamic terms. Okay, it has dynamic terms. So the dynamic term is terms that is relates to your what it changes with time. Okay, so we have this term. So this equation can be used to design controller. However, in those who are familiar with control theory, you may know that designing controller for time varying quantities such as AC sinusoidal current or voltage is more complex. So we do have time varying quantities here, or AC sinusoidal quantities. Our current, voltage, EMF, all are sinusoidal quantities. On top of that, in PMSM, there is one more complexity. That is especially in the salient pole type synchronous machine, where we have the inductance not same in all rotor positions. Since air gap is small along the D axis or at the face of the next to the pole face, we get much higher D axis, much higher inductance because it has low reluctance here compared to the interpolar part where the air gap is much large. That's the salient pole synchronous machine. And since we also have PMSM machine such as the interior type PM machine, which behaves like a salient pole synchronous machine. So in those PMSM, also the inductance will have a similar thing. Like only difference is that in IPMSM, the D-axis inductance is actually smaller compared to Q-axis inductance, which means the reluctance in D-axis is higher than the reluctance of Q-axis. So we'll explain that a little bit later again, but we just need to know at this stage that the inductances, we get high inductance here and low inductance in there in conventional machine. In IPMSM, it's just opposite. So that means our inductance are actually a function of the position, rotor position. We'll get certain value of inductance at this position, and the value will become different at 90 degree at this position. So if we measure the self and mutual inductance of a salient pole machine and plot it against the rotor positions, theta, you will see this variation for both self-inductance and mutual inductance. And the self-inductance or mutual inductance, you can notice that they will have a DC average value. So if we do a Fourier analysis of these two waveforms, we will see it has a DC component and some harmonic component. And that harmonic is actually a second order harmonic or 2 theta component. In mutual inductance, also same thing, but the DC component will be half of the DC component of the self-inductance. And again, it will have a second harmonic term. So these second harmonic terms, while these second harmonic terms, we can understand quite easily. If we have one pole pair, we always see 2 peaks in our inductance, right? The maximum value will, inductance will be maximum here. It will be minimum here. It will be maximum here. And again, minimum here. That means we see 2 peaks, okay? 2 peaks in one cycle or in 360 degree. So that means it is a second order harmonic, so which appear here as that second order harmonic in the inductance. So our self and mutual inductance are actually function of theta. That means in our voltage equation, not just time varying quantity we also have position varying quantity. So it makes it even more complex to design controllers for a when the quantities varies this way. So how can we simplify this type of equations, and how can we then apply known classical linear control theory to design controllers? So that brings us to the concept of reference frame theory. And it is when we apply reference frame theory to a equation like this, you will soon see that it actually becomes mathematically a DC equation, DC quantity equations. And then the controllers become very simple, like designing control of a DC motor with DC quantities. This all happens only mathematically, you have to remember. In reality, nothing happens. We still have AC quantity. Our inductance is still varying in with position, but mathematically we can manipulate it while designing the controller. And so that's the first point of or key point that we must understand when we want to control modern three-phase machine. And this concept is actually true for even conventional synchronous machine, induction machine, and also obviously the PMSM. So what is then reference frame theory? The concept is actually not very difficult to understand. It's kind of you are transforming three-phase to two-phase mathematically. Okay, you know in our machine we have ABC three-phase winding. So if we apply this transformation, they will become two-phase D and Q, and that two phases again need to remember is that these two phases only happening mathematically, not actually physically. You are not transforming anything. You are only transforming the quantities mathematically. And we can, that when we transform it mathematically, we can imagine instead of three winding, that means we have now only two windings. And one is along the D axis, other one is in the Q axis. So D and Q axis, in fact, has come from our salient pole machines, D and Q axis, where we have minimum air gap. We define that as D axis and interpolar part as Q axis. So same concept here, the D and from the same concept actually come the D and Q axis. But, and also you need to remember that in the, when we discuss a synchronous machine, we started our discussion with the uniform air gap machine, and then we expanded it to salient pole machine. But when we do control, we do the opposite way. We develop the model for a salient pole synchronous machine, and then we can simplify it to uniform air gap machine, because this model is more complex for salient pole machine. So that's why the derivation is all with for a salient pole machine, which will later can be modified to uniform air gap machine as well. Now, so that, as I said, that we can imagine we had three phase, but after applying the transformation reference frame theory, we can convert it to mathematically to two phase, and our D and Q axis or D and Q windings, so you can imagine as the two windings now, they could be attached to either to the rotor or to the stator. If we consider that these DQ windings are now attached to the stator, that means they are stationary, they are not rotating, then we get the stationary reference frame. Okay, so if we consider that our DQ axis is attached to the rotor and rotating with the same speed as the rotor, then we get a rotor reference frame. And if we consider that our DQ axis is actually rotating with synchronous speed, then it is a synchronous reference frame. For a synchronous machine such as Pmsm, the synchronous reference frame and rotor reference frame become same because it rotates only with synchronous speed. But for an induction machine, the synchronous reference frame and rotor reference frame are different. As some of you know, the induction motor rotates at a speed other than synchronous speed. But for synchronous machine, fortunately, we don't have to distinguish between rotor and synchronous rotor reference frame and synchronous reference frame. And mostly we'll be talking about synchronous reference frame. So when we apply the so how do you do this transformation? I said we do it mathematically. So what is this transformation actually? So to look at that, it's actually a quite simple matrix transformation. It has a standard form. Okay, cosine cos theta minus 120 degree, cos theta plus 120 degree, minus sine theta minus sine theta minus 120 degrees. So it's quite easy to understand. So if we multiply our ABC quantities, this ABC quantities could be current, volt. Could you please mute your mic if you have background noise? So these ABC quantities could be your voltage, it could be your current, it could be your flux linkage, it could be any of the three-phase sinusoidal quantities. You multiply those quantity by this matrix, okay? And then as a result, what we get, we will get a quantity in d-axis, q-axis, and zero-axis, okay?
Oh,
so in that, could you please mute if you have a background noise? Thank you. So that theta, how do you define this theta is, as you know, that d theta dt is the omega. So that means if we integrate the speed with which our reference frame is rotating, we get a position, and that's that theta, okay? And this omega is the electrical speed. This omega could be the synchronous speed, it could be the rotor speed, it could be even an arbitrary speed, or it could be even zero. So based on what value of omega we have, theta value will change, and we will get different type of transformation or different type of reference frame, as you have seen in the previous table. If we have zero omega, that means stationary, it's not rotating, so theta becomes zero then, provided initial angle is also zero. So theta is zero. Then if you put theta zero in this matrix, obviously you will get certain constant numbers here, right? Cos zero will give you 1, sine theta times 0 will give you 0, 0, and cos 100 minus 120 degree going to give you half, sine will give you √3/2, and so on. So these numbers will become a constant number here. When that means in stationary reference frame, all these quantities simply becomes a constant number. And then that transformation is known as Clark's transformation. In fact, when this concept of reference theory first invented, it was invented as a stationary reference frame, and it was developed separately. So that's known as Clark transformation. Later, another scientist invented that if theta is not zero, but relates to a certain speed, then that transformation can still be used, okay? And that concept later was combined together to one single reference frame theory. And the second scientist who discovered this transformation, his name was Park. So that's why when we use the matrix in which theta comes from the synchronous speed, electrical synchronous speed, that transformation is still referred as Park's transformation, okay? So stationary reference frame referred sometimes as Clark transformation, and synchronous frame transformation referred as Park's transformation. So as we can convert our ABC quantity to DQ by using the inverse of this matrix, we can also convert our DQ quantity back to ABC, okay? So that's the basic principle of reference frame transformation. Convert ABC to DQ or DQ back to ABC. Synchronous reference frame known as Parkes transformation, stationary reference frame, when theta is 0, we get the Clark's transformation. Now, how it helps us? So our voltage equation, if you recall, was that our inductance is a function of theta, I, A, B, C, and P, A, B, C. These are time varying quantities. And in PM machine, obviously, the EMF, EABC is coming from permanent magnet, and inductance drops relates to the current induced flux linkage. This, of course, we can combine back to the two flux linkages, that current induced and then PM induced flux linkage can be combined together, and that is referred here as lambda ABC. So note that lambda ABCI means current state or current induced flux linkage, but lambda ABC means it includes both current and the PM induced flux linkage. So we have a little bit simplified, and ABC means that we have IABC, lambda ABC means we have lambda A, lambda B, lambda C, okay? Just because it's easy to write this way, otherwise it's going to take me pages and pages. It takes so many space if you want to write it as a matrix. So that's why the simple, it is a simple representation. And we also need to know that in this equation, actually the resistance is, which is shown as RS, it's actually again a matrix, a diagonal matrix with value RA, RB, RC. So these are the three-phase resistances, and they could be of the same value. Usually that's what it is. RA, RB, RC are equal in a balanced three-phase machine. But just for understanding, so know that these are the three-phase resistances. And in our current induced inductance, current induced flux linkage, actually the current time the synchronous reactance, but this synchronous reactance LS is theta dependent, and it includes all the self and mutual inductance. In fact, this is a matrix, okay, which you will see a little bit later. So with this, now we are going to apply our transformation. So when we said applying transformation means we are multiplying our ABC quantity by that matrix, and IABC, we are multiplying it by the same matrix, and the lambda ABC also we are multiplying it by this matrix. So we're going to use Parkes transformation, as I said, for synchronous machine. Synchronous rotating frame is the most useful. So we applying Parkes transformation, and after doing lots and lots of maths of matrix manipulation, matrix algebra, etc., at the end, what you're going to get is your VQ and VD voltage equal to the current ID IQ times the resistance. This is a resistance matrix, remember, times the speed. This is your electrical synchronous speed to D and Q axis flux linkage now, and d dt of the two flux linkage lambda d lambda q. This has become now lambda d lambda q, but with matrix, because of the matrix manipulation, we have this additional term as well. Okay. So, and those two flux linkages, D flux linkage and Q flux linkage, they are in fact the Q axis inductance time IQ and D axis inductance time ID. Sorry, this would be ID, not IQ. ID time lambda PM. Okay, and so just hang on. this is. So that in that again, in the d-axis, we have our PM flux linkage, okay? So this, what is this LD and LQ? Are they still theta dependent? So to examine this, we have to go to the next slide. So our inductances were, if you remember, self-inductance was function of theta, mutual inductance was also function of theta. But now if we apply our transformation to this inductance matrix, so we have for A phase, B phase, C phase, mutual inductances and the self-inductances, okay? So in this matrix, if we apply the transformation, so that the first one was the Parkes transformation, and second, this is the inverse of the Parkes transformation. So if we multiply, because this is the term which is going to come in our, when we apply here, okay? This is what will appear if we replace the lambda D and lambda Q in terms of this inductance. That is, sorry, if we replace our lambda ABC as the L time I D I Q, if we replace as this in our these equations, then in the transformation, when we do all the various matrix manipulation, this will appear, okay? So when we do this multiplication between three matrices, the resultant will be a LD and LQ term in our left-hand side. And this LD and LQ term actually consists of L0 and L1, 3/2, and also in LQ we have L0 plus L1, 3/2. 3/2 is coming from the transformation, okay? And L0, L1 coming from our self and mutual inductance, but they are no longer, the theta term is no longer there. Theta term has disappeared when we did this matrix manipulation. So now our LD and LQ are just two constant values, okay? This is the DC component, this is the amplitude of your second harmonic. So they are constant. And this is the leakage inductance. So leakage inductance is always present. So if we can neglect it if we want, but you can see that LD and LQ has now become actually theta independent. So that's the beauty of reference frame theory. It has converted the theta dependent inductances to two constant inductance, LD and LQ. It has also, in fact, converted the voltage, VD, VQ, ID, IQ, even the flux linkage, lambda D, lambda Q, all this quantity has actually become time independent with a little bit of, if you do some maths there using certain numerical values as your sinusoidal current and sinusoidal voltage, and you do that matrix transformation, you will be able to see that omega t term disappears and there becomes DC quantities. So now we have voltage equations which includes resistive drop, inductive drop, flux link, additional flux linkage term like this, but they are all in DC. They are no longer time varying, theta varying quantities. And this is actually known as the DQ model. They can still include the time variation of a DC quantity, DIQ dt, such or as an inductive drop, but the theta it is no longer theta dependent, and it can handle dynamic conditions. Also, this same equation, we can even write a whole thing in terms of resistance and inductance without considering or substituting the flux linkages. So what these two flux linkages are, the lambda Q is actually LQ IQ, and lambda D is the LD ID. Sorry, this is ID, not IQ. Okay, this is a typo here, lambda PM. So that this is the flux linkage along the D axis. This is the flux linkage along the Q axis, which is going to give us the total flux linkage. And if we replace them here in this equation, or even here in these equations, we can find a voltage equation and which are in terms of inductances, and also this omega E time lambda PM is actually nothing but the EMF. EMF, if you remember, was coming from lambda PM, and lambda PM, flux linkage lambda PM time omega E is the EMF. Okay, if you remember the DC motor, in a DC motor, it is the flux times speed, which gives, and a constant, which gives you the EMF. So now it becomes very similar to a DC motor. In a DC motor, you could have a resistance, you could have an inductance, because in DC motor, your winding has an inductance, right? So we usually have a RA and the LA, and then you have the EMF. So RA, the armature resistance, LA, armature winding inductance, and EMF. So this equation is very much similar to the DC equation, DC motor equation. And those who are familiar with control theory, probably you know how to design controllers for a RL load. You also know how to design controllers for DC motor. So all those knowledge can be now bring into here. We have a RL load kind of, and we have like a DC motor, all quantities are DC. So we can actually apply those knowledge to our model and design classical PI controllers even for our motor. Also, these equations can be now represented in the as a equivalent circuit. So this is the dynamic equivalent circuit or DQ equivalent circuit. Okay, so it is simply translate to a circuit. So we have a resistive drop, so that's the RS. We have an inductive drop, that's your inductance, and flux linkage times speed always gives you a voltage. So that means this is a voltage source. Okay, so that's what we have here. Similarly for your, sorry, this one was for the voltage equation. So that, and this one is for the Q axis. So we get two equivalent circuit, one for D axis, one for Q axis, and they can be drawn straight away from these equations. We can also even find out what is, how they will look like if it is steady state. So in steady state, there will be no change in your current, right? So steady state DC circuit inductance drop will become 0. So this, in steady state, this one becomes 0. The LDI/dt term becomes 0. So we'll have a resistive drop. We have omega E lambda D, but lambda D is equal to LDID and lambda plus lambda PM. So we will have this term from here. And similarly for the VD, again, resistive drop remains, and omega E times lambda Q becomes omega E LQ IQ. So this is the steady state equation for our for the DQ model. we don't need to go back to our equivalent steady state equivalent circuit anymore. We can just get all our information, dynamic as well as the steady state, from now using the DQ model. In fact, we can even draw phasor diagrams if we want to, using these equations for understanding of how the voltage and currents are. We'll do that in a minute. But before that, let's look at how is the power, what happens to power and torque in terms of these DQ quantities, because that's what we are interested, right? If you want to control your generator, wind generator, you want to control the power. If you are a motor engineer, motor drive engineer, you would like to control your torque or speed. So we are interested to know what happens to power and torque in DQ transformation. And for that, again, we start with the basic. We start with the instantaneous power of three-phase VA, IA, VB, IB plus PCIC, which we can also write in as in matrix form, right? And then if we apply our transformation to Park's transformation to this voltage matrix and Park transformation to our current matrix, and do a lot of matrix manipulation or matrix maths, matrix algebra, at the end, what you're going to get is a simple thing, 3/2 VQ IQ plus VD ID. So that's the input power. And we know what is VQ, what is VD. So we can replace the VD, VQ from our previous voltage equations that we have seen in the last slide. And if we substitute them here, the power equation will become something as shown here. So it may look like at first go something very complex, but just look a little bit more closely and you will see clearly what these three terms actually mean. Remember, this is our input power, okay? Input power to the motor. So the first part is resistance times square of the currents. So this is actually the loss in your motor, the resistive loss in your motor. Second term is the voltage drop in the inductance times the current. So this means it is a power related to the inductor. And what's the power related to inductor? Perhaps most of you know, it is the reactive power. So this together, these two terms, which is with the inductance, this is actually reactive power in your machine. And the last term, the third term, which is omega E, synchronous electric speed, time flux linkage in d-axis, q-axis current, flux linkage q-axis, time ID current. This is actually the real power, or the power which in a motor will convert to a mechanical work or torque, or in a generator, this is the power which you will be interested. This is what's going to power your load. So that means this is the developed power, real power. And we are only interested into this term when we want to look at what happens to the torque as a motor engineer. So that developed power is, that's why 3/2 omega E lambda D IQ minus lambda Q ID, the simple equation. And if we divide this power with speed, we should get our torque, okay? So power divided by the synchronous speed, but this synchronous speed need to be the mechanical synchronous speed, remember. So omega E was electrical synchronous speed. So if we divide your electrical speed by the pole pair, you get the mechanical synchronous speed. So you divide your developed power by the mechanical synchronous speed, and you will get your torque. So only difference in the torque equation is that now omega E has been cancelled out. Instead, we have now the pole pair in our equation. And we can even write this equation in terms of our inductances. So and flux linkage lambda D, as we know, is actually lambda PM time LDID, and lambda Q is LQIQ. So if we substitute those things here, we'll get our torque equation in terms of inductances, LDLQ, and the PM flux linkage. Now, if you look again closely, you'll see that the first term is due to so torque here has two components. The first torque is coming from due to the magnet's flux linkage. And that's why this term is called magnet torque. And the second term is because of the difference in the two inductances, which is this difference actually comes due to the difference in your reluctance in diagram. So that second term is actually the reluctance torque, which we have seen in our salient pole machine. So this is exactly the same torque, only now in terms of IDIQ quantities. And if we have a uniform air gap machine or surface type PMSM, LD will be equal to LQ. And that means this term will not exist. We will only have magnet-induced torque in surface type PMSM. Also, if you look closely this torque equation, you can see that it comes from the current and comes from the magnet. So those of you who have remembered DC motor torque equation, you may remember that it is a constant, torque constant KT times the flux times the current. So exact same equation we are getting, that this like a DC motor equation. We will have a constant, which is that 1.5 times pole pairs, a flux coming from the field or rotor, in our case, magnet flux, times the current, the armature current. In case of synchronous machine, obviously the stator is the armature current. So this becomes like a DC motor torque. And it's again, the controlling this torque, we can use our knowledge of DC motor control that we can apply our classic linear control theory of PI controller design here. So that's another good thing. One thing to remember is that in the salient pole synchronous machine, the LD is bigger than LQ, whereas in a IPMSM, it is opposite. LQ is bigger than LD. So if we want to make this torque additive, you want torque to be as large as possible, right? So you want this term to be additive, not subtractive type. So if you want to make it additive, that means since LD is smaller than LQ, this term is negative. So how can we make this still additive? If we make our ID current negative, okay? So in a PM synchronous machine, especially in IPMSM, you operate with negative ID current and positive IQ current, so that this term becomes additive. You can probably see it in the the phasor diagram. And that phasor diagram has come from those steady state equation, as I said previously. There's a few things to notice here is those angle. Remember the delta angle? Delta angle was between the EMF and the terminal voltage. That delta angle, still the same delta angle, okay? So EMF is along Q axis. So delta angle is actually angle between Q axis and the voltage phasor, phase voltage phasor. The gamma angle is the current angle. We have defined it previously. It is the angle between the current phasor of your phase current and the q-axis, okay? And power factor angle is still same between your phase voltage and phase current phasor. So that's the power factor angle. Your flux linkage, lambda PM flux linkage is along the d-axis, and which induces your UMF, which is along the q-axis. EF is your EMF coming from the lambda PM. So that relation is also still true. And we can, this omega E LD is actually could be thought of as a reactance in a phasor context. So that's omega E LD ID should be with the, if it's reactance, it should be with J, right? So J means it's should be 90 degrees to the d-axis. So it should be along the, the XDID. So XDID should be along the q-axis when we have a J. So that's XDID is here, but remember our ID current is negative. So it is facing opposite to your EMF, okay, in your phasor diagram. And XQIQ should be along the d-axis when we have the J, the imaginary reactance. So it is 90 degree to the q-axis or along the d-axis. In fact, from here, we can also write our voltage, VD, VQ voltage or IQ, ID current in terms of the voltage phasor, the actual phase voltage phasor and phase current phasor, and using these known angles. And if we replace or substitute these quantities back into this torque equation, it will be the same torque equation that we have found in our classical discussion of conventional synchronous machine. And that we can, in fact, have the same torque equation in terms of also current angle gamma if we use the only current angle substitution here. If we use the voltage or the delta angle substitution, then we get that classical equation, which we derive in our first lecture, in the second lecture. And with gamma angle, we get the same torque equation, but in terms of current angle. So DQ model, when we say for PMSM, it consists of those two VD, VQ equations, the voltage equations, the torque equations. And from the phasor diagram, we can also conclude that the q-axis voltage and d-axis voltage are 90 degrees to each other. Similarly, q-axis current and ID current are 90 degrees to each other. And if we find the amplitude of them, that should give us the peak value of our phase voltage. If we do with the current, we get the peak value of our phase current. Okay, so these are the most or the important key points here for understanding the control DQ model. So that maybe we can take a break here for 5 minutes, and then we will discuss the FOC or field oriented control. Okay, I can see there were some. Is there any questions? If you have question, you can also post that in the chat window. So we're going to take 5 minutes break, which is going to be in your time 11:40. Okay.
Okay, madam.
Okay, madam. Okay.
All right. So we'll come back at 11:40 your time. Is that okay? The time? Like I don't know. I'm just looking at my phone and I thought it's 11:35. What's your time there?
Yes, ma'am. It is 11:35. Yes.
Okay, so then we'll come back at 5 minutes later. Means 11:40.
Yes, ma'am. Sure, ma'am.
Okay. All right.
Thank you.
Can we be back? Hello?
Yes, ma'am.
Are we back?
Yes, sure, ma'am. You can start, ma'am. I think. Yes. I think no question has been posted till now.
Mhm. Do you have any questions, participant?
Yes, ma'am.
So I can see a question from Amit. What is the basic concept behind the rotor magnetic flux and why it is along the axis? And the second question, if we are going to model a PMSM machine, then rotor magnetic flux should be kept constant. Okay, good question, Amit. So we go back and quickly look at the model. It's here. So lambda PM means this is just same concept as the lambda F, or number of turns in your A phase multiplied by flux coming from the rotor PM. So that's the lambda PM flux linkage. Exact same concept as a field flux in a conventional synchronous machine, or as in the even in DC machine. Okay, so that's the flux linkage. And why we keep it in the d-axis? Because if you remember, our the definition of d-axis was along the where we have the pole face. Okay, so that's the definition of d-axis is along the magnetization direction of the magnets. So that from there, so we say that flux linkage lambda PM is aligned with the d-axis, and the back EMF that it produces is 90 degrees to it, so it is along the q-axis. And of course, yes, in a PM machine, lambda PM is constant. It doesn't, theoretically, it should not change. Okay, we have a constant value. If you look at the datasheet of a BLDC machine or PMSM, they usually give this value. Okay, they may give it you as a EMF, back EMF constant. In fact, back EMF constant is nothing but lambda PM, maybe in a different unit. Sometimes they give it in as a volt by kilo RPM or something, but ultimately you can calculate always out what is the lambda PM. So this is along the axis, and for PMSM it is constant. It is along the axis because the way the d-axis is defined is along the where the magnetization is in your rotor. So now with the DQ model, we are ready to look at how to design the controller. So we'll first explain the fundamentals of field-oriented control. In fact, now all modern drive systems uses field-oriented control. So if, after graduating, if you go and work in an industry, refinery, whether it is you work in the oil or in the like the or any other industry, process industry, where they may be using the drive systems or variable speed drives, there is more than likely you will come across the field-oriented control. Okay, so that's why perhaps good idea to have some fundamental knowledge, even if you're not planning to become a machine drive researcher, but this could be useful for your professional career, what we're going to discuss now. So we'll do the fundamentals first, and then at the end, you today's tutorial, in the second half of the today's tutorial, you will be able to build a field-oriented control for PMSM using MATLAB Simulink. So if you have access to MATLAB Simulink, you will be able to do step-by-step as Dr. Chu will show you along with him. So instead of just watching what he's doing, perhaps it will be more interesting if you can do along with him. And that's why if you have access to MATLAB Simulink, please, during tutorial, open them up Okay. So to understand control, let's look at how the Pmsm is driven first. I mentioned in the beginning that Pmsm actually cannot be driven by just connecting to three-phase supply. You have to connect it through the controller or the inverter. So even if you have three-phase AC supply, you have to actually then rectify it and get a DC bus, and then DC bus goes, and then DC bus connects to an inverter, and the output of which is connected to the Pmsm. If this motor is driven, or this motor is for an EV, electric vehicle, then this DC part comes from a battery. Okay, you don't need a rectifier or a three-phase supply. You can directly connect the battery here. So hopefully some of you are familiar with power electronics inverters. I don't have time to go through the inverter basics, but those who are not familiar with inverter or power electronics, you can obviously find how it works, what it is from even a textbook, okay, or do a Google search, they will tell you. Now, anyway, so that's why we need the inverter, because we haven't said this when we discuss synchronous machine, that a synchronous machine cannot start by itself. It doesn't have self-starting capability as the induction machine. So we have discussed the rotating magnetic field, and we have said that the stator gives you the rotating magnetic field, and you have rotor has the pole north and south. So stator north and south is rotating. So if imagine the north of the stator pulling the south of the rotor, and that's how the rotor starts to rotate, and we get the torque. So that's a basic concept, and that's correct. However, we need to remember that our rotating magnetic field is rotating at the synchronous speed, that's the electrical synchronous speed, quite fast. Whereas the rotor, it's a mechanical thing, right? It could have very large inertia. So if we imagine that rotating north pole of your stator, which is trying to pull the south pole of your rotor, before it can pull to a certain position, the north pole of your stator will change to south because it is so quick, the rotation. So that means if your rotating magnetic field is turning at a very high speed, this large inertia rotor cannot be pulled along with it easily. So then what do we do? In conventional synchronous machine, you have damper winding. So the synchronous machine actually starts like an induction machine, and then when it is aligned with the stator rotating field, the rotor aligns with the rotating stator's rotating field, then it starts to rotate at the synchronous speed, because we are providing the field current to the rotor, so it can rotate at synchronous speed. Whereas in induction machine, a rotor cannot rotate at synchronous speed, because if it starts to rotate at synchronous speed, then there will not be any induced voltage or current in the rotor of the induction motor, and it will fail to produce any torque. Whereas in synchronous machine, we are not inducing any current or voltage in the rotor. We are supplying it through the field winding. So that's why it can rotate at synchronous speed. But now in a Pmsm, we don't have any damper winding, nothing, no such thing, but it's still the same thing. If your rotating magnetic field is turning at the 50 hertz supply, means 1500 RPM, and your rotor has a big inertia, then it will not turn. So what we do, if we use an inverter, the advantage of inverter is that the output voltage frequency at voltage at the output of an inverter can be varied or controlled as we like. So we can start with a very low frequency supply here. So a very low frequency means, let's say, it starts with 1 hertz. When your that means your synchronous rotating synchronous speed will be for 1 hertz, very slow, and your rotor is also rotating slowly, right, because of the inertia. So that means from the start, the rotor magnetic or the rotor itself and the rotating magnetic field are aligned, and the speed increases as it accelerates. So how speed increases your rotating magnetic field? By increasing the frequency. So that's the main task of the inverter when it is with a variable speed drive. You get variable voltage and frequency at the output, and so that the motors, a synchronous motor, can start without any trouble. Now, to what voltage, what frequency we want to get it comes from the controller. The controller we'll discuss a little bit later what inside this. Output of the controller is actually the sine, could be sine wave PWM, or it could be space vector PWM, which are pulses for these 6 switches. Okay, so that's the basic structure of a Pmsm drive. You must have an inverter, you must have a DC bus, which may come from 3-phase supply or from a battery, and you must have this controller. So inside this controller sits that field-oriented control. So we are interested to control the torque or speed, and so our controllers will be according to our requirement. Now, we could also have direct torque control, which is an alternative way of controlling the torque. In fact, in field-oriented control, or sometimes it's referred as vector control, we in fact controlling also the torque, but not directly. We control the torque via controlling current. Okay, so field-oriented control is an indirect torque control method. We control torque indirectly via controlling the current or flux. In PM machine, usually you don't control the flux, especially the rotor flux, but you can control stator flux. Okay. So what is inside a FOC? You could have a speed controller. For example, let's say it is driving an electric car. So you press your accelerator and you want to drive your car at 50 km/h speed. So that means that's your speed. That's the speed at which you want to drive the car, which will translate to a rotational speed for your wheel, which will translate to a rotational speed for your motor. So that's our speed command, okay, to the controller. And that goes, then this speed controller could be a PI controller. So if it is a feedback PI controller, we'll need a feedback signal, the speed. So that speed comes from your speed signals comes from the motor. So how do you get this speed? Usually we have a position sensor which sense the rotor positions theta. So that rotor position is also required in our Parkes transformation. If you remember that cos theta minus 120 degrees. So what are those, what that theta is? In fact, that is the electrical rotor position of your rotor. So if we have a sensor and that can give us the mechanical rotor position, multiplying it by pole pairs, we will get the theta electrical position, and we can use this to get our Parkes transformation. So this, all these controllers and everything nowadays sits in a microprocessor. So these are like kind of codes. Because all these things could be done in the microprocessor. So they are, nowadays hardly people use hardware PI controllers, all software. So all these things actually sits in the microprocessor. You only need to get the theta signal from a sensor, and then this multiplication happens in your code, and this transformation happens in your code because it's just matrix algebra. And from there you get your ID current and IQ current. You also need to sense that the actual current, the three-phase currents, IA, IB, IC. Usually IA and IB is sufficient. IC can be calculated, since we know for a balanced machine, IA plus IB plus IC is 0. So if we know IA and IB, we can always calculate out C. So we only need two current sensors and a position sensor, and the rest of the things actually in your microprocessor. And then of course you have the inverter in hardware. Okay, so that two current and the theta, and then you apply DQ transformation, you get your ID and IQ current as to feedback current. And that theta can also be converted to speed. As we know, d theta dt is the speed. So if we know theta, we actually also know the speed, and we can find electrical speed or mechanical speed, whatever we want. Again, just by in our code, by doing an integration or differentiation or multiplying by pole pairs, all can be done quite easily. So that's the theta actually gives you that omega m, the feedback speed signal. And this is a PI, if it's a PI controller, output of it is the torque that is required to run the motor at this particular speed. And the torque, this is our reference torque then. So to produce this reference torque, we need to have certain ID current and certain IQ current from our torque equation. So that ID and IQ current references can be generated based on what operating condition we want to drive our motor. So those ID, IQ current are our reference coming from the torque reference. And then they go to two current controllers. Again, PI current controllers it could be. And output of those two current controllers is PD and PQ reference. And then if we apply the Parkes inverse transformation, then we will get a PA, VV, VC, the reference voltage at the output. And that reference voltage then can be applied to sine PWM generator, which will produce the pulses for our inverter. And output of the inverter will be the required voltage and current to produce this torque, which will drive the motor at the speed. So that's what basically the field-oriented control is, current control. sits inside or as a nested inner controllers, and outside sits a speed controller or a torque controller. Sometimes we may eliminate speed control. We can just directly have a torque control. One thing we have to remember is that in our torque equation, remember these are PI controllers we are designing. And how do we design them? As I mentioned, we can actually design them considering our system is like a RL load. Okay, those who are familiar with control system, you know how very easily you can design PI controller for RL load. So if we look at it, our DQ equation, the first part is actually a RL load. And the second half, we have an additional term. And this term, if you look closely, this is actually in terms of IQ current, whereas voltage is VD voltage. Similarly, in the VQ voltage, we have a term which is in the D axis, ID current. So that means these two equations, VD and VQ, are coupled to the D and Q axis, since it has both terms, D axis term as well as Q axis term. So if we consider this coupling term outside of our control, then the designing the controllers are very easy, just like RL, designing a controller for RL load. And that's what usually we do. So we design PI controllers for our current, but this coupling term we add later. So this is known as dynamic decoupling of the PD-VQ voltages. So we calculate these two terms outside of the controller, and then we add them at the output of the PI controller is this part, okay? And then we add this part outside, and then we get our reference voltage PD-VQ, and then we apply our inverse Spark transformation to get the reference IA/IB/IC, which becomes reference of your, if it is a PWM generator, it becomes the reference for your PWM, SPWM, or we can convert them to space vector modulation. Now, one couple of things we have to remember, that is that we cannot just keep increasing our current to whatever value we like, or similarly, you cannot keep increasing our voltage to whatever value we like. We can't do that. The voltage has its own, the motor has its limitation. It can go only up to its rated voltage and rated current. So we have to limit our voltages and currents in the controllers. So this current limit comes from that relation which I have mentioned previously, squaring the or finding the amplitude from the IDIQ current. You can get the amplitude of your current phasor, and that current phasor cannot exceed the rated current of your motor. So this current phasor or current amplitude must be always less than the rated current. And similarly, the voltage, same, it must be always less than the rated voltage of your motor. So the current, actually, this current equation, if we plot them in a DQ plan, IDIQ plan, it's actually a circle, okay? So the current limit translates to a circle in the IDIQ plan. And the voltage limit, if we replace the VD/VQ from our DQ model, the equations, and if we ignore the resistive drop, then this voltage equation actually becomes like a equation of ellipse. Okay, that's the equation of ellipse. But the voltage equation actually dependent of the speed. In fact, as the speed increases, the available voltage in your system reduces. So that's why the ellipse for different speed becomes smaller and smaller. As the speed increases, the voltage limit shrinks because we do not have the voltage, available voltage start to be not sufficient as the speed increases. So why so? Maybe I will come back to this a little bit later, but maybe this concept is more important at this point. So remember our EMF? EMF is directly proportional to speed. So if your speed increases, your EMF will start to grow. Okay, EMF will start to grow. And your voltage equation or the voltage phasor, if you remember, it is the function of it is the combination of your EMF to reactive drops, which is your terminal voltage. But as the E grows, your voltage phasor will start to grow, right? But as I said, we only have limited voltage, so that the ellipse that you have seen is the boundary. We cannot go beyond this, otherwise motor will be burned. So then how do we keep this growing voltage phasor within this limit? So there comes that concept of flux weakening. So if you have a DC machine, you would have simply apply or reduce your field current, and you would have reduced your lambda PM, and you would have reduced your EMF. Even in a conventional synchronous machine, you could have done that because you have the option of reducing the flux, rotor flux. But now in a PM machine, lambda PM is fixed. We cannot reduce it. But if we look at our phasor diagram, you will see that component IDXD, this reactive drop of the D-axis inductance, is opposite to the EMF, okay, phasor. So if we, as the EMF grows, at the same time, if we can make this negative drop grow in the opposite direction, then the resultant voltage can be kept at the limited value or the limit value. So that's how you can do a flux weakening in a PM machine. By increasing the negative ID current, we can make this item become more and more negative so that resultant voltage phasor still remains within the limit. So you can see here, the EMF has grown to a very large value. But at the same time, since the negative ID has grown, so that drop was increased, but in the opposite direction of EMF. So that's why the resultant voltage phasor remain within that limit. So that's how we do flux weakening and keep the voltage phasor within the required limit. If we do not do that, the available voltage will not be or available voltage will not be sufficient. That's what was represented by this shrinking voltage limits ellipses. And also the other thing to understand is that you may want to run the motor at certain operating conditions or to get the optimum performance. So if you have the surface type PM machine, if you go back to our torque equation, so if you have a surface type PMSM, we don't have this component at all, right? The LD is equal to LQ. We only torque component is lambda PM IQ. So we do not need a ID current actually in a we do not need to have any value for ID current in a surface type Pmsm. So that means the ID current reference could be 0. Okay, so that the controller keeps always ID to be 0. So that type of control is called ID 0 control. Okay, and ID 0 control gives us or best for surface type Pmsm. It also good if we go back and look at the phasor diagram here. So if you do not have ID or ID is 0, that means your IQ current is your IS, because ID 0 means IS and IQ same, right? So when IQ is 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 your IS and IQ is same, then your obviously will not have this component as well, and the voltage phasor is going to be here. So when voltage phasor is here, the angle, the power factor angle can be maintained with a minimum value, or you can even make unity power factor if we can make the voltage, this voltage phasor go very close to the q-axis or even into the q-axis. So ID 0 control for surface type can give you a much higher power factor as well. So that's why for surface type, ID 0 control is preferred. But for IPMSM, as we know, we in fact want to have flux weakening. So we need a negative current. We may also want to get the maximum torque with minimum current. Okay, so that's known as maximum torque per ampere performance, or MTPA. So MTPA is preferred control technique for IPMSM, in which ID current is not 0 but have a certain negative value. And what that negative value, it can be calculated using that what is maximum torque for minimum current by differentiating the torque equation in terms of the either current angle gamma or in terms of current itself, and then equating it to 0. So if we do that, we will be able to find a certain value for ID current. And that's, if we put these numerical values here, we'll find certain numerical value. And that becomes the ID current reference. So if the operating point, MTP operating point, or maximum torque per ampere operating point could be this A. And then you can clearly see we will have a certain Q-axis current and a certain negative ID current. Okay, so for IPMSM, thing to remember is that for IPMSM, MTPA is preferred, and in MTPA, ID current is not 0, but it has a certain negative value. There are also other type of operation we may want to run the machine with, such as maximum efficiency, or if we are running the motor at the speed above the base speed, then we have to operate with flux weakening. So when we do flux weakening, that means we have to increasing the negative ID current. So if this is your MTPA point, and MTPA is operation is when you have constant torque. So remember, in your EV torque speed characteristic, we have constant torque, and then the torque starts to fall to give us that constant power operation range when we go to the speed higher than the rated speed. So up to the constant torque, you operate along this MTPA trajectory. as the torque max. If you're operating with the maximum rated torque, then this is your operating point. If you do not meet the maximum torque, especially if you're doing an industrial drive, maybe your load has reduced, so you may need half the torque. Then you will be in a lower point somewhere here, but still along this MTPA trajectory, okay? But if you want to now run your motor at the speed above the rated speed or base speed or at constant power speed range, CPSR, you have to apply you have to apply flux weakening. That means you have to increase your negative ID current. So, but you still need to be within your current limit cycle. Okay, so that's when you do flux weakening, you start to increase your ID current. But if you increase your ID current and you want to be within the current limit, you may have to now reduce your IQ current. So you move from MTPA point along this red line. So this is the flux weakening current trajectory. So this is, you can find various value of ID and IQ current along this line, along this, at this periphery of the current limit cycle. And so that's the flux weakening trajectory. Then sometimes for some PMSM machine, what happens is that the center of the ellipse, this point, either could be outside of the current limit cycle, this cycle, or it could be inside. So if it is inside, that means we can even get a maximum torque under limited voltage condition, because under flux weakening, you have limited voltage, but you want to may want to get the maximum torque. So that condition gives us another trajectory known as maximum torque per volt. So you can run it in flux weakening, and then you can, if you have arrived at this point in your operation of the motor, you may run along the MTPP or maximum torque per voltage trajectory. So these different things or different trajectory actually may be required by the operation or to get the best performance out of your PMSM. And accordingly, you can generate the ID IQ reference currents. That's what we have seen here. We said that current reference generator. So what are those? What should be the IQ reference? What should be the ID reference? They could be determined from these operating conditions, in whichever you are operating. Accordingly, you can calculate out the reference value for your ID and IQ. Usually, IQ is determined from the torque itself, because as you can see, the torque equation, IQ is directly related to your torque. Okay, IQ is directly related to your torque. So usually the speed controller output gives you the torque, which directly translates to your IQ reference. But the value for ID reference could be different depending on what operating condition you want to drive the motor. If it is a SPMSM, ID reference could be 0. If it is IPMSM and you want to run it at MTPA, maximum torque per ampere, then you calculate out that particular value and will be here. If it is flux weakening, then the ID current will increase according to the flux weakening trajectory here, based on what speed you are. Okay. And last one is if you can also get maximum torque with limited voltage if you operate along that third trajectory. So this is something interesting to know, is the comes from also the flux weakening. The maximum, what is the maximum of flux weakening? If we can reduce the lambda PM to 0 by applying this negative LDID, we'll get the limit for our flux weakening, right? And if we get that, in fact, ideally, it will be like you could have like constant power speed range for infinite speed. But obviously in a real machine, that's not possible. But this theoretical limit is actually useful. So if lambda PM is equal to LDID, that's our limit for flux weakening. And that means the ID, if in that limit, if ID current becomes equal to our rated current, then that is the maximum theoretically possible ID current for a maximum theoretically possible flux weakening. And this current is known as characteristic current, which can be quite easily calculated by dividing the lambda PM by LD. This also interesting to know that that characteristic current is actually the center of your ellipse, okay? And your center of the ellipse, whether it will sit outside of the current limit circle or at the boundary of the current limit, it can be actually decided or determined during the machine design, because you can design in such a way, okay? So this could be sometimes an objective in machine design, especially in optimization, which we'll discuss in tomorrow's lecture. If we can make this ratio equal to our rated current, that is that the ellipse center, and will lie on the current limit cycle. And this is the optimum or theoretically optimum point for constant power speed range. And theoretically, then we can get infinite constant power speed range. But of course, in a real machine, it never happens. You can't do that. Even if you design it to be your characteristic current to be here during the design, but in reality, this always falls at certain speed because of the iron losses. In all these, we have neglected our losses: iron loss, mechanical loss, your even the resistive loss. So in reality, because of the loss, you cannot be able to keep the power constant for infinite. At certain point, it will fall. So you can see a few results from experimental results of how this trajectory following can be done through the control. In these are some of our results from our laboratory actually. So you can see how the motor operated along the anti-PA. Then it has gone to flux weakening, and then it operated along that maximum torque per voltage trajectory. You can also see how the speed has accelerated from 0 speed to a 4,000 RPM by the speed controller. And the ID current is following the reference. The blue one is the actual measured current, red one is the reference. So the PI controllers are designed such a way that they are following those references very closely. So during MTPA, we have certain ID current, negative ID current value. And then during the flux weakening, the ID current has become higher in the negative side. So before it was about 0.8, later it has become minus 1.1 or so. That's the flux weakening. And then once it has, the speed is reached that it's steady state, so current settle down on whatever the torque has demanded, the value. Similarly, the Q-axis current, you can see that Q-axis current has this very similar characteristic of the torque. As I said, torque and IQ current is exactly the same. The profile, the current profile and the torque profile. So it was maintained at 1 ampere, and then as in the flux weakening, the IQ current will start to drop, and then it will settle down whatever the load has demanded at steady state. So that brings us to the end of this 2 hours lecture of the morning hub. In summary, we have looked at the reference frame theory. We have developed the DQ model and understood that by using DQ model of 3-phase complex machines such as Pmsm, controller design can be made simple. And when we use DQ reference frame, in fact, all the quantities becomes DC quantities. Therefore, the control also becomes like a control of a DC machine. And we control the torque in FOC control by indirectly controlling it through the current. But one of the things for FOC is that you must have a position sensor, and a very good precise position sensor is required, as we have to apply our Parkes transformation or inverse Parkes transformation. But it gives a very good dynamics, and you can accelerate your motor to whatever, how fast you want, and it is quite smooth control. Okay. Any question?
Madam, there is a question in this chat box.
Okay. I can't see it. Is this the Amit's question, or is there some more of? There's one question from Amit, and I think I have answered.
Yes.
Yeah, I have answered that already before
Okay.
our yeah. Is there any other question? Okay, so there is a, I don't know whether it's a question from Devasis. Do you like to know the direct axis inductance? Why it is less? That's what you want to know? Is it Devasis? That's what you want to know?
Yes, madam. Yes, madam.
Okay, so let's look at the IPMSM. I thought I have a good picture, but looks like it has some missing. Anyway, so let's me go back to one of the IPMSM pictures so that I can explain to you. we have started with this one yesterday. So this is your real Pmsm machine, right? So your flux, remember the flux goes, maybe not this one, there's another, you want to see the flux path so that you can understand better. Let me go back to the flux path. Maybe this one, yep, this one will do, yep. So this is, if you look at, this is the Pmsm machine, right? You can see how the flux is crossing the magnet, then it goes to the air gap, and then it goes to stator, goes to stator yoke, comes back, meets the magnet again, and closes the path, right? So that's how it the flux path is. In the flux path, we have the magnet. Okay, this is the d-axis. We define this as our d-axis and that as our q-axis. So in the d-axis, that means this is the d-axis, okay? And that's your q-axis. So in the d-axis, sorry. Oh, no, that's the d-axis, sorry. See, so along the d-axis, and that's your q-axis, sorry. Along the d-axis, the flux has to pass the magnet and the air gap. And magnet's reluctance is same as air. Okay, so that means it see a much large reluctance on its path when it has to cross the magnet. Whereas in the q-axis, that is here, okay, along that line, here it doesn't have to cross the magnet. It just needs to cross the air gap alone, which is a very, very small air gap, as you know, 0.5, 0.1 millimeter. So in the q-axis for IPMSM, the reluctance is very small. That means inductance is large. LQ is large compared to LD. Whereas in a salient pole conventional synchronous machine, if you remember it was the other way around. The d-axis was much where you have in the d-axis it sees the small air gap, and the q-axis it sees the large air gap. So in the conventional machine, so d-axis has large LD, whereas q-axis is smaller inductance. But IPMSM, it is opposite. Since in the d-axis, the flux has to cross the magnet and then go to the air gap. So magnet itself is like a big air gap. So that's why the inductance of d-axis is smaller. Okay.
Thank you.
Is there another question? Okay, there are a few questions, I think. Okay. Oh no, so that's the same one from Amit. Yep. Anything else? Any other question from anyone else? No?
I think there is a question, Madam. Jibon?
Yes, sir.
Hello, Jibon?
I think no
more question?
No more question is there.
Jibon, you can conclude.
Yes, sir. Okay, thank you, ma'am. Thank you for such a nice discussion and such a nice lecture. So, thank you so much, ma'am.
Okay, so we will break for 1 hour, right? What time are we coming back for the tutorial?
Okay, 1:35.
1:30, yes, yes.
1:35. So that will be in our time 7 p.m. 7:05 p.m. Okay.
Okay.
We'll
Okay.
see you then that time. Thank you.
Okay, thank you,
Thank you.
ma'am.
Thank you.
Thank you so much.
Thank you.
We'll send the link for the second
Yes,
half.
please. Yes, please.
Okay.
Yes.
Okay.
You may have to change back the host. Otherwise, I am going to end up meeting for everyone. Okay. Thank you.
Okay. 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 Thank you, ma'am. Manjot.
Sikhe sir, can I leave or I have to stay here?
Yes. You can leave. Okay. Thank you for your time.
No problem, sir. No problem. Okay.
Okay.